Hey everyone, welcome to tutorial number 8. In this video, I'll discuss the buffer object and demonstrate some of its common uses. So far, the audio examples in this series have focused on generated sound, like sine waves, sawtooth waves, white noise, and so forth, but we haven't really dealt with recorded sound yet, and for this, we use buffers. Generally speaking, a buffer corresponds to a location in your computer's memory that's used to hold an ordered sequence of values. In the context of digital sound, buffers are usually used for holding, recording, and playing back sampled audio. So let's get started. Buffers are server-side objects, which means we'll need to boot the audio server before we can do anything useful. To load an audio file into a buffer, you can use the read method, which allocates a buffer on the audio server and reads your sound file into it. At minimum, read expects two arguments. The first argument is the server onto which the buffer will be loaded. In this case, and in most cases, this is the local audio server stored in the global variable s. The second argument is a string that represents the path of your sound file. On my desktop, I've got a folder called Sounds, which has a few sound files I'll use for this tutorial. And this is also a good time to point out that your sound files should be in either AIF or WAV format. I'll load the file called car1, which sounds like this. And I happen to know that the path for this file is /users/eli/desktop/sounds/car1.aiff. Remember that a string is delineated by an enclosure of double quotes, and also make sure to use exact spelling and capitalization. Okay, so let's stop here and run this line. In the post window, this is what you can expect to see if you've done everything correctly. If you misspell your path name, SuperCollider will let you know. As a convenience, we can use the play method to hear the contents of a buffer. But with this approach, all you can really do is verify that your sound file has been loaded successfully. It's also important to know how to clear and remove buffers once you've created them. If you want to clear the contents of a buffer, but not remove it from the server, we can use the 0 message. And now if we play B0, all we hear is silence. We've cleared B0, but we haven't removed the allocated buffer from the server, so we can fill it with sound once again using the read method on the allocated buffer, like this. If you want to remove a buffer from the server entirely, we use free, just like we do with synths and groups. Now this buffer is completely gone, so if we try to play it, or read a file into it, we get an error message. And since we're on the topic of freeing buffers, if you ever want to remove all allocated buffers and start with a clean slate, you can use the class method freeAll, like this. So that more or less covers the basics of adding and removing buffers. So let's get that sound back. Now, if you're like me, you'll get really tired really fast of having to type a long string every time you want to read an audio file into a buffer, especially if your sound is buried 12 folders deep and, has a really long path name. So I'm going to demonstrate a useful shortcut. Instead of manually typing the path, you can drag and drop a sound file into the editor, and it'll automatically be converted into a string representing its path. And while I'm at it, I'll also load the sounds called car2, car3, and bike into their own buffers. Okay, cool. So now that we've got a few sound files loaded, let's talk about some fundamental attributes of buffers. First, every buffer has a certain number of frames, and this number corresponds to the length of the buffer. If you want to know the number of frames in a buffer, we can just use the numFrames method, like this. And we can see that buffer B0 has 132,313 frames. Frames are similar to samples, but not quite the same. To illustrate the difference, I'll segue into another fundamental attribute, which is channels. Like frames, every buffer has a certain number of channels. Using the numChannels method, we can see that buffer B0 has 2 channels. This is because the original audio file is a stereo file, and therefore has 2 channels. The read message detects this and automatically allocates a buffer with the same number of channels. So here's the difference between samples and frames. In the case of a mono buffer, or in other words, a one-channel buffer, the number of samples is the same as the number of frames. With a stereo buffer, there are 2 channels, so there are actually twice as many samples as there are frames. Buffers can have any number of channels, actually, not just 1 or 2, so the equation to remember is the number of samples in a buffer is equal to the number of frames times the number of channels. As we'll see later on, it's important to be aware of how many channels you're dealing with, because buffer UGens won't work correctly if you're inconsistent when specifying the number of channels you're working with. Speaking of monophonic buffers, let's take a quick detour before we continue talking about fundamental attributes of buffers. Suppose we have a stereo sound file, but we only want to read one of the 2 channels into a buffer. We can do this by using the read channel method, which is almost the same as the read method, but includes an additional argument for specifying the number of channels. Channels is specified as an array. The array 0, in this case, will read the first channel, usually considered the left channel, and the array 1 will read the other channel. Now, if we take a look at the level meters, we see that buffer B0 plays out of both speakers, since we've loaded a stereo file into it. But buffer B4 is a one-channel buffer, so we only see and hear one channel of audio. Okay, moving on to more fundamental attributes. If you ever need the length of a buffer in seconds, you can use the duration method, like this. And that's pretty straightforward. One very common and important attribute is buffer numbers. Whenever a buffer is loaded onto the server using read channel, or any other method of buffer allocation, SuperCollider assigns to it a buffer number, or bufnum, as it's more commonly called. Bufnums are integers, starting with 0, that are automatically assigned in ascending order when a buffer is created. If you want to get the bufnum for a particular buffer, we use the method bufnum. We can see that the bufnums have been assigned according to the order in which we created these buffers. However, bufnums might not always be in perfect ascending order, depending on how and when you create and remove buffers. But, as we'll see later on, you don't really have to worry about how SuperCollider assigns bufnums. The important thing to remember is that at any given moment, each buffer on the server has a unique integer associated with it, and that you can get that integer using the bufnum method. The last attribute I'll discuss is the buffer sample rate. All sound files are recorded and exported at a specific sample rate, and buffers reflect these sample rates. The audio file in buffer B0, and in fact most of the other sounds in this folder, have been exported at 44,100 samples per second. And the server sample rate is the same, so I'm in good shape. It is possible to have buffer sample rates that are different from the server sample rate, so long as you're aware of the difference and take the correct measures, so that your sounds aren't unintentionally resampled. We'll deal with this a bit later. In summary, you can use the query message as a quick and convenient way to see many of these fundamental attributes all at once. So that's about it for buffer fundamentals. There are 2 things I'd like to talk about before we dive into buffer UGens. One is how to read only part of a sound file into a buffer, and 2 is how to read many sound files onto the server all at once. To read part of a sound file into a buffer, we can use the 3rd and 4th arguments of the read method, start frame, and num frames. To demonstrate, I'll revisit the motorcycle sound, which is currently stored in buffer B3. Let's suppose I only want to read the first half second of this sound file. I'll specify 0 as the starting frame, and for the number of frames, I can just specify half the server's sample rate. Alternatively, let's say I want to read just the tail end of this sound file. First, I'll check the number of frames in the buffer containing the full sound file, which happens to be 264,599. I'll pick an arbitrary start frame somewhere close to the end, and I'll use simple subtraction to determine the number of frames between this frame and the end. However, because the index of the first frame is 0, not 1, This means the index of the last frame is actually the total number of frames minus 1. So the responsible thing to do here is to subtract an extra frame. Okay, technically this might not be necessary. I think there's a chance SuperCollider might anticipate this error and handle it for us, but even so, it feels like a safe thing to do. So let's talk about how to load many sound files all at once, instead of having to type them one at a time. There are, in fact, lots of different ways to do this, and most of them involve some kind of iteration. One fairly simple option is to store your buffers in an array, so that each buffer is addressable by a unique index. For this example, I have a folder containing a chromatic scale of desk bells. And I'll start by creating an empty array, which will be used to hold our buffers. I'm also going to use an instance of a class called pathname that acts as a reference to the folder of bell sounds. If you send the message entries to a pathname, it will return an array of pathnames representing the files within that folder. Now all I have to do is iterate over the folder entries using do, similar to what we saw in tutorial 6. I'll iterate over these paths, and on each iteration I'll add a buffer to the array using the current path. I'll need to use a method called fullPath to convert a pathname into a string. And that's really all there is to it. We can see that the bells array is now filled with buffers. And we can refer to individual buffers using the at method, like this. Even quicker is the syntactical shortcut using square brackets. Keep in mind that there is a limit on the number of buffers you can load onto the server, which you can get by evaluating s.options.num buffers. The default is 1024, but if you need more than that, you can change the maximum number of buffers by setting this attribute equal to a new value, evaluating this line, and rebooting the server, which I won't actually do because I don't need to. And if you find yourself loading a really substantial amount of sound files, you'll probably see the server become inactive for several seconds, and the server will come back online when it's done. And this is normal because that's what happens when you slam scSynth with hundreds of commands all at once. That about covers buffer fundamentals. Let's now turn our attention to manipulating buffers with ugens. There are two ugens commonly used for buffer playback: PlayBuf and BufRd. The main difference between these two is that PlayBuf will read through a buffer automatically according to a given playback rate, whereas BufRd doesn't have a rate argument and instead relies on an audio rate pointer into the buffer for sample playback. I'll deal with PlayBuf first, and I'll create a synth to demonstrate. At minimum, PlayBuf needs to know two things about the buffer it's playing: the number of channels and the bufnum. Since I'm only going to be dealing with stereo sound, I'll specify 2 channels. For the bufnum, it's possible to provide it explicitly like this, but of course this is a poor choice because it means that this synth will only be able to play buffer B0. Much better is to declare a bufnum argument and specify the bufnum when the synth is created, like this. Now we can use the same synth to play different buffers. On the other hand, it's not possible to declare an argument for the number of channels, as we can see from this error message. Now the reason for this is that the number of audio channels in a synth can't change dynamically, and instead has to be a fixed known quantity when the synth is compiled, so the num channels argument can't be modulated. Speaking of, another common pitfall can arise when the number of channels of the PlayBuf doesn't match the number of channels in the buffer. Here, I'll try to play buffer B4, which is monophonic, and SuperCollider reacts with a polite message that the number of channels don't match. But don't get used to this courtesy because there are many situations in which a buffer channel mismatch will cause a synth to fail silently without any indications or any error messages. Okay, so let's develop our synth some more. To continue, let's take a look at the node tree. where we can see that even though we're not hearing anything at the moment, we've got a pile of synths that have built up on the server. Okay, so first things first, let's clear out all this junk with s.freeall. So what were those synths doing on the server? As it turns out, just like with nggen from tutorial number 4, PlayBuf has an inherently finite duration, and therefore has a done action associated with it. When PlayBuf reaches the end of the buffer, it checks its done action to determine what kind of action to take. The default value is 0, which means when PlayBuf finishes, it takes no action and just sits on the last frame indefinitely. If you want the synth to free itself after it's done playing, you specify done action 2. In fact, I'll declare an argument for done action, so that we'll have the option to choose different types of actions for different situations. Now this synth will free itself automatically when PlayBuf is finished. Let's add an argument for the playback rate. Rate is interpreted as a ratio, so 1 is the normal sample rate, 2 is twice as fast, and 0.5 is twice as slow. However, simply specifying the playback rate with a number isn't foolproof, and this has to do with buffer sample rates, which I mentioned earlier. For instance, if your buffer sample rate is different from the server sample rate, the buffer will be resampled and you won't get the results you might expect. To demonstrate, I've got a modified copy of car1 that's been exported at 96,000 samples per second, as we can verify with query. But if we play this buffer using our synthdef, specifying a rate of 1, PlayBuf resamples the buffer to fit the server sample rate, which causes a pitch and time shift. The most sensible way to deal with this problem is to use one of several convenience ugens designed to access a buffer's attributes. In the help documentation, we can find these ugens under Browse, Ugens, Buffer, and finally Info. In this case, we want to use a ugen called BufRd.ar, which outputs a ratio based on the buffer and server sample rates so that the buffer will play back at its original correct speed. BufRd.ar and these other 5 info ugens only need one argument, the buffnum for the appropriate buffer. And now our synthdef can handle buffers with different sample rates, and the rate argument behaves consistently. Getting back to PlayBuf now, trigger and start pause allow you to specify a starting frame and give the option of jumping to that frame by sending a trigger. Keep in mind that if done action is 2 and PlayBuf reaches the end of the buffer, the synth will free itself and therefore won't be triggerable. This particular synth will start a half second after the beginning and won't free itself if it gets to the end. We can jump to the start position like this. Loop is the last argument we haven't talked about. If loop is set to 1, PlayBuf will loop through the buffer and ignore its done action. Loop can be changed while the synth is playing, just like other arguments. If we set loop to 0, the synth will evaluate its done action as soon as PlayBuf reaches the end of the buffer. To play a sound backward using PlayBuf, we provide a negative rate and make sure we start at the last frame. But again, keep in mind that to specify the last frame, we need to subtract 1 from the total number of frames because the frame indices start with 0. But even this doesn't work, and I'll tell you why. We're starting at the last frame of the buffer, which is PlayBuf's cue to check its done action, and that happens to be 2. So this means when we instantiate the synth, it actually frees itself immediately. We can correct this by specifying the start position to be 1 frame earlier. I want to return to the idea of playback rates for a second because it needs to be said that ratios are not the most intuitive way to think about pitch, especially if you're interested in chromatic harmony. For this reason, there's a method called MIDI ratio, which converts a transposition in semitones into an equal tempered ratio. For example, a shift of 12 semitones up would be an octave. So 12.MIDI ratio returns 2. Okay, almost, but it's close enough. Likewise, 12 semitones down, or negative 12, returns 1/2. A perfect fifth is 7 semitones, so there's the equal tempered ratio for a fifth, and so on. So with MIDI ratio, it becomes very easy to transpose your sounds by semitones. So that's essentially how PlayBuf works. Here's a quick example that's a little more interesting and a little less clinical. I'll first create a group, and I'll put 3 synths into it, each with a different buffer and a different playback rate, and I'll loop them. I can simultaneously change the rate of all 3 synths by sending a message to the group. I can set all 3 synths to play the same buffer. And I can send messages individually too. Here I'll randomize the rates so that they all fall out of phase with one another. And last, I'll turn off looping for all 3 of these synths. Cool. Okay, so let's now turn our attention to BufRd. BufRd starts with the same 2 arguments as PlayBuf, the number of channels and the buff num. The third argument must be an audio rate signal, which will be used as a frame pointer into the buffer. So let's make another variable called pointer. Suppose we just want to read through this buffer once. The simplest way to do this is to use line, which goes from point A to point B over a given duration. The read pointer for BufRd must run at the audio rate, so I'm choosing .ar. We want to start at the 0th frame and travel to the last frame. And this is a good opportunity to revisit the buffer info ugens. Here we can use buff frames, making sure to subtract 1, and then for the duration argument we can use BufDur to ensure that the line takes the correct amount of time to travel from start to finish. And for good measure, I'll specify done action 2 on the line so that the synth will free itself at the end. Maybe we want some flexibility in where line starts and ends, so I'll declare some arguments. Now we can play the file forward or backward. To loop a buffer, we need to choose a ugen other than line because line isn't capable of looping. Phaser is usually an excellent choice for this because it's a linear ramp oscillator with inputs for start, end, and rate. I'll just provide a 0 for the trigger argument because I don't plan on re-triggering phaser, and I'll go right to the second argument, which is rate. And once again, this is a great opportunity to use buff rate scale. With phaser, I can change the start and end points, for example, to only read the second half of the file. Or I can choose a more specific range of frames. And I can change the rate too, just like I did with PlayBuf. I find that phaser is usually the right tool for looping through a buffer using BufRd, but there are a couple alternatives to phaser. In particular, there's sweep and there's LF-saw, and you might find both of these useful in some situations. But BufRd is even more flexible because you can use any audio rate UGen as a frame pointer, so long as that UGen has an appropriate output range. For example, I can read a buffer forward and backward sinusoidally by using sinosc as an audio rate pointer. With sinosc, I'll set the initial phase offset to be 3 pi over 2 so that the sine wave starts at its lowest point, which corresponds to the beginning of the buffer. And I also have to use the range method to make sure that the oscillator has an appropriate output range. One of my personal favorites, you can use a noise generator as a buffer playback pointer. Using a linearly interpolating low-frequency noise generator like LFD Noise 1, you'll hear random sections of the sound file at random speeds, sometimes forward and sometimes backward. With multiple synths, each playing a different sound, you can get some interesting layered effects. The higher the frequency of the noise generator, the faster the playback pointer will move, and this will give your audio a more chaotic and glitchy sound. That's about it for tutorial number 8. I haven't discussed the flip side of buffer playback, which is buffer recording. PlayBuf and BufRd each have a corresponding UGen designed to write data into a buffer, much in the same way that these two UGens read buffer data. They're named recordBuf and BufWrite, respectively. All of the help files in this video are worth reading if you'd like to learn more, and, as always, I encourage you to experiment. In the next video, I'll talk about SuperCollider's MIDI classes and give a few demonstrations of how to get SuperCollider to communicate with external MIDI devices. I hope you enjoyed this video, and thanks for watching.